Welcome back, everybody. Today I'm going to talk about a style of classifier that's very different from support vector machines. The classifiers that we will cover for the next couple of weeks are based on probability and using statistical distributions. Now, one aspect of probabilistic data is sometimes you have a point in feature space that doesn't just have one class. Like, suppose that your data is a set of adult men and adult women, and for each of them you have just one feature, their height in feet and inches. And you want to train a classifier that takes an adult's height and returns a classification, man or woman. And all right, suppose that someone gives you a test example and says, I have a 5'5" person. Is that a man or a woman? So what do? Well, one thing to keep in mind here is that in your feature space, you typically have two training points that have the same location but different classes, because there are lots of 5'5" men in the world and lots of 5'5" women. And the issue, well, first of all, you're going to have two different points at exactly the same location with different classes. But more than that, you can have overlapping probability distributions of classes. So first issue, multiple sample points, possibly including multiple training points that have different classes, could lie at the same point. So for that reason, we want a probabilistic classifier that will tell me, given a 5'5" adult, what is the most likely sex for that person. But the bigger issue is one of overlapping probability distributions. If we take a height axis, and we define the PDFs for what we believe is the distribution of women's heights. Maybe those look like they're on a bell curve. Maybe they're normally distributed, at least to a first approximation. And so the problem I'm asking here is, someone is 5 feet 5 inches tall. What should I predict about that person's gender if that's all I have to go on? Well, the best guess we can do is we can say at that height there are more women than men, so I'm going to guess it's a woman. Of course, I could be very wrong about that. 40% of the time it'll be a man, but that's the best I can do with such limited data. So when you have these overlapping distributions and someone says, here's a test point, give me a classification, you're going to give a classification that you can't be certain is correct. The data overlap in ways that you have to guess, in a sense, but you might be able to, for instance, give a probability of your guess being correct in addition to giving the guess itself. And that's what we're going to learn how to do today. In order to get deeper into this, I'm going to give you a somewhat more complicated example, which is cancer diagnosis. Now, there's some subtleties. One of the subtleties is the fact that people are much more likely to not have cancer than to have cancer, and that's something you have to take into account when you're trying to decide the probability that someone has cancer. So let's just suppose, this is obviously an exaggeration, but suppose that 10% of the population has cancer and 90% does not. Now, suppose that I make a table of probability distributions. for the calorie intake of two types of people. We'll look at the calorie intake of people who have cancer and the calorie intake of people who don't have cancer. And we will think of these probabilities of P of X conditioned on Y. X is the number of calories per day that someone is eating. Y is whether or not they have cancer. And to keep things simple right now, I'm not going to use a continuous distribution. I'm going to use a discrete distribution with just 3 bins. So our calories come in one of 3 categories, and that's the X variable. You could have a person who's consuming less than 1,200 per day. You could have a person who's consuming 1,200 to 1,600 per day, or you could have people who are consuming more than 1,600 per day. All right, so I looked at a bunch of people who have cancer, which we will call the condition y equal to 1, means somebody has cancer. And we discovered that of those people, 20% of them are eating fewer than 1,200 calories per day. 50% are eating between 1,200 and 1,600, and 30% are eating over 1,600. And we did the same thing for people with no cancer, which we'll call the condition y equal -1. And we discovered that 1% of them are eating fewer than 1,200 calories per day, 10% are eating between 1,200 and 1,600, and 89% of them are eating over 1,600 calories. By the way, I made these numbers up. Please do not take these as medical advice. And so again, the numbers in the table are the probability of a specific number of calories conditioned on whether or not you have cancer. Okay? Numbers are. Before we go on, I want to put these populations together, the cancer and no cancer populations, and just ask what is the possibility of eating a specific number of calories for an arbitrary human being now. What is happening? Okay, now my pad is acting very weird. Sorry about this. It thinks the pencil is charged, so why does it not want to work? All right, I think we're back. Sorry about that. I want to remind you from your knowledge of probability how we compute P of x given this table. P of x is, well, specifically the probability that a person randomly selected from the population is eating less than 1,200 calories a day, or the probability that that person's eating between 1,200 and 1,600, and so on. So given a particular X bin, well, I have to consider two types of people, the ones who have cancer and the ones that don't. And the way we do this is that we're going to multiply the probability that a person has cancer by the conditional probability of them having a certain value of X given that they have cancer. And then we're going to do the same thing for people who don't have cancer and add them all up together, and that'll give me all of the people who are eating fewer than 1,200 calories a day. So I hope this formula looks familiar. And to give a specific example of that, if we look at the middle bin, the bin of people who are eating between 1,200 and 1,600 calories per day, then, well, we have that of the 10% of people who have cancer, 50% of them are in this bin, and of the 90% of people who don't have cancer, 10% of them are in that bin. .14. So here's the question. Here's the classification problem. Suppose you meet a guy who is eating X equals 1,400 calories a day. And you want to guess whether he has cancer. Again, remember, this is a classification problem. I want to classify people with cancer. All right. How could we figure that out from this table? Well, if you're in a hurry, you might say, oh, look, 50% of people with cancer, 50% of people with cancer are eating that many calories, but only 10% of people who don't have cancer are eating that many calories, so he probably has cancer. What's wrong with this reasoning? Exactly. There's a lot more people who don't have cancer than who do, and I didn't take that into account at all with this reasoning. So that reasoning is just wrong. What is the correct way to figure out whether the probability that this person has cancer? Yeah, Bayes' theorem. Thank you. So Bayes' theorem is a way to massage this data to take into account the fact that you are just much more likely to not have cancer than to have cancer. And so we're going to compute the probabilities that we really want to know are, first of all, the probability of having cancer conditioned on eating a specific number of calories. And just a reminder that this is sometimes called the posterior probability in Bayes' theorem. And Bayes' theorem says that this posterior probability is equal to the following ratio. You take the conditional going the other way, that is the probability of eating a certain number of calories if you have cancer. You multiply it by the likelihood of having cancer, and then you divide by the probability of eating that many calories. And I want to single out one of these three expressions as having a special name. This one is called the prior probability. The probability of having cancer, basically, is the prior probability here. And likewise, we can also apply Bayes' theorem to not having cancer. So the probability that I don't have cancer, given a certain calorie intake, also a posterior probability, is computed the same way, except that I replace all the y equals 1s with y equal minus 1. And notice that both denominators are the same. That'll be important later. All right, so let's put some numbers to this. Specifically, we're just going to look at the case where the calorie intake is somewhere between 1,200 and 1,600. And plugging the numbers from the table into these formulae, you're going to get that the probability of having cancer given 1,400 calorie intake is 0.05 divided by 0.14. And the probability of not having cancer is 0.09 divided by 0.14. And so taking that number, the probability of having cancer, given an intake of 1,400 calories, is 14ths, or approximately 36%. So the bottom line is we probably should not diagnose cancer. This person probably does not have cancer. By the way, I want to point out that these two probabilities add up to 1. They have to add up to 1 because either you have cancer or you don't have cancer. You can't be both ways. You can't be neither way. Question? Is there a particular reason why we chose y to be 1 and negative 1? No. Could have been 1 and 0. That's fine too. All right, so I just told you this person probably does not have cancer. But wait, we're not done yet. Because we are assuming that we want to maximize the chance of correct prediction. But we don't always want to maximize the chance of a correct prediction. A lot of the time we think that a false positive is not equally bad as a false. They're both a little bit bad, but if someone has cancer and you miss the fact that they have cancer, they might die. If someone doesn't have cancer and you tell them they have cancer, there are consequences too, but maybe not as severe. And let's suppose, for instance, that the thing that we're looking at is a cheap early test to diagnose cancer. And the idea being that if this cheap test comes out positive, then you're going to go on to do a more expensive test, like a biopsy. All right, so risks we're weighing off are, if you have a false negative, you might miss your cancer and die. If you have a false positive, you might get an unnecessary biopsy. Obviously, the dying is the worst outcome. And so we want to express the fact that we would much rather have a false positive than a false negative if you're doing cheap cancer screening. So there's a way that we encode that called a loss function. These loss functions are very widely used in statistics. And a loss function specifies how bad is it if my classifier predicts class Z, but is wrong in the true classes Y. So I'll give you an example of the loss function we might use for cancer screening. We could choose a loss function that is 1 if we predict cancer, but the patient does not have cancer. 5 if we predict no cancer, but it turns out the patient does have cancer. And 0 if z is equal to y. So the first line is basically saying, okay, sure, a false positive is bad. We want to penalize it. The penalty will be 1. The second line is saying, but a false negative is really bad. And so we want to penalize it more, in this case, 5 times as much. And the last line, I just want to say that this should essentially always be true of loss functions. We're not going to see any counterexamples this semester. When you make a perfectly correct prediction, the loss should be 0. Otherwise, you shouldn't call it a loss function. All right, so if we take this loss function and apply it to the cancer screening, well, what we're trading off is there is a, if we guess that there's cancer, if we guess that there's no cancer, there's only a 36% chance that we're wrong, but if we're wrong, then we're going to incur a loss of 5. And numerically, that's worse than if we predict cancer, and we're 64% likely to be wrong, but if we're wrong, we incur a loss of only 1. So in this case, with this loss function, we recommend further cancer screening. Go on and get that biopsy. All right, so a few quick definitions regarding loss functions. The loss function I just showed you is asymmetrical. So a loss function is symmetric if false positives and false negatives both have exactly the same penalty. It's asymmetric if you punish one more than the other. Now, the most common loss function used in machine learning and statistics is just called the 0-1 loss function. The 0-1 loss function is a function that is just 1 for all incorrect predictions. And 0 for all correct predictions. So that is obviously symmetrical. False negatives, false positives are penalized equally 1. So although the 0-1 loss is still the most commonly used loss, there are many applications where you want an asymmetric loss. Cancer screening is kind of an obvious example because cancer is very serious. A different example, not as serious, is spam. You did spam detection in homework 1. Well, generally it's considered that putting a good email into the spam folder is worse than putting spam into your inbox. So you would probably want to use an asymmetric loss function for spam as well. Yes?
Why would we ever have a use for a symmetrical loss function? Would we just not need a loss function at all? It seemed like the problem previously we needed to introduce a loss function was because having false negatives is much worse than having false positives. So why would we use a symmetric loss function?
Well, I think that if you're using the 0, 1 loss function, I think that's equivalent to what you mean when you say don't use a loss function at all. Yeah, so you can interpret using a 0, 1 loss function as just another way to say don't use a loss function at all if you prefer to think of it that way. There isn't a difference. Yeah.
I wonder if this loss function is asymmetric, and does it always mean it encourages the philosopher to always predict the patient has a cancer?
Well, yeah, that is definitely a real problem that you have to worry about. If you make your asymmetric loss function asymmetric enough, you might find that your classifier just predicts that everybody has cancer to be safe, and now you have a useless classifier. Yes, that can happen, and if that happens, it either means that your asymmetric loss function is too asymmetric, or it means that your screening test just isn't good enough to be used at all. That's happened sometimes. Any other questions about this before I go on? We're going to get deeper into what is risk and what is decision theory next. But hopefully these examples I've laid out motivate why we want to think about this stuff. Yeah?
I wonder how can we optimize this classifier with this loss function?
How do you optimize this classifier with this loss function?
Because it only has some numbers, but there are still more variables for us to calculate the gradient.
Oh, there's no gradients going to be involved here. We're going to do something very different. So this is going to be very unlike SVMs. There will be no gradient descent. We're going to do something completely different. But I'm going to develop that over today's lecture and Wednesdays. So bear with me, please. Yeah?
Is there any way to find optimal way, optimal of the loss function possible use one time here? How you compare whether two times is better or not?
Whether two what?
Two times, like the loss function. 2, 1 is false positive. So there are a lot of combination here.
Mm-hmm.
Find the optimal.
Oh, are you talking about multi-class problems when you have more than two classes?
How to find the best number? For example, you use 1 and 5 here.
For the loss function.
Yeah.
This is completely an application-dependent thing. So that might come, for instance, from doing if you want to be cold about it, do an economic analysis of which is worse, somebody dying or somebody getting a biopsy. That's one way you could approach the problem, is by calculating the costs and choosing the appropriate ratio if you're trying to minimize. Obviously, when it comes to questions where you're actually weighing a human life, it's harder, but it has to be done, so people find ways to do it. So we're going to assume now that, well, let me define a mathematical function that is essentially a mathematical abstraction of a classifier. So I'm going to have a function called little r that maps a point in d-dimensional feature space to either a plus or a minus 1. And that mathematical function is what I'm going to call a decision rule. And a decision rule, in a sense, is another word for a classifier. I mean, they're not exactly the same. A classifier is usually a computer program that you wrote. A decision rule is just the function that's computed by that computer program, a mathematical abstraction of the computer program to just a math function. Little r is that math function. So that function takes in a feature vector x and maps it either to 1, meaning it is in the class, or minus 1, meaning it's not in the class. And we're going to use that function now to compute what's called the risk. And this is kind of important, so let me highlight it. The risk for a decision rule R is the expected loss. All right, when I say expected loss, I'm taking the expectation over something. I'm taking a mean here. Over what? Over a probability distribution of all the possible values of x and y, feature vector and label, that I could possibly expect to get. All right, so I would suggest you want to memorize this definition. So the risk is the expected loss. The risk is the expected loss. The risk is the mean loss. Let's put that in terms of mathematics. Given a decision rule R, the risk, which I'm going to call capital R, well, capital R of little r is the expected value of the loss over all of the possible training and test points I might ever encounter. So x and y, you should think of those as being random variables from a joint probability distribution of feature point, comma, class. All right, let's write this out in detail. What's the expected loss? Well, it's the sum over, I'm summing over little x here. This is the set of all possible values that the random variable big X can take on. Here I'm assuming a discrete probability distribution. We'll do continuous later. So for each possible discrete value of the random variable x, I'm going to look at the loss if that my decision rule has on that particular feature point times the probability that that feature point actually should be considered in the class, plus there's a second loss for if my decision rule, sorry, there's a second summoned for the case where the true label is not in the class. So the true value of y is, nope, I'm not in the class. All right, so we sum these all together, and at the end we multiply by probability of x equal little x. Sorry, that's in the sum, actually. All right, so that's the expected loss over all possible combinations of x and y you could get. And I want to point out that the two probabilities inside the big paren are both posterior probabilities. So there's a second way I can write out this risk of the decision rule by plugging in Bayes' formula and expressing those posterior probabilities in terms of prior probabilities and class conditional probabilities. If I do that, it's going to look like this. So first, I'll consider all of the cases where we have a point in the class. And then I'll consider the case of all possible points that are not in the class. And in both cases, I'm summing over all the different possible values of x that might come up for that class. All right, two different expressions for the risk, one which focuses on the posteriors, one that focuses on the priors and the class conditional distributions. Both of these are going to be useful later in this lecture, so they're both going to come up. Which line? Yeah, thank you. Sorry. All right, again, -1 there. Is that the one you were pointing to, or do I have a second mistake? Okay, great. All right. Now, we can apply this risk to any decision rule, but we're particularly interested in the decision rule that minimizes the risk. And that's got a very special name in statistics. It's called the Bayes decision rule. Sometimes it's also called the Bayes classifier. And that is the function, the decision rule, I'll call it R star, that minimizes the risk. So by the way, maybe you haven't all seen the word functional before. A functional is a function that takes a function as its input. So you might notice that maybe it's new to you, the idea that a function can itself be a parameter to another function. R is a function, of course. It's the decision rule. But this is a perfectly valid thing to do, is feed a function into another function. Now, what I want to do is I want to figure out for this definition of risk, what is the Bayes decision rule? The Bayes decision rule is, I just want to reinforce the assumption that the loss is always 0 for a correct prediction. So we're just going to hard code that assumption into our class. You never penalize a perfectly correct prediction. Assuming that's true, then, for the discrete distribution case, we can write out the Bayes decision rule explicitly like this. We either choose 1, it's in class, or -1, it's not in class. When do we output 1? We output 1 if this expression is greater than this expression. And if that's not greater, then we output a -1. So where did that come from? Well, it came from here. So what I decided is that I just want to make this as small as possible. So what I do is I say, well, my prediction can be a 1 or it can be a -1. So one of those two terms is always going to be 0. Let's compare which of the two non-zero terms are going to hurt me more, give me a bigger loss, and try to choose a prediction to make sure that I never incur the bigger loss. And so this conditional here just tells me which of the two terms are bigger, and therefore I should choose the prediction so that the bigger term never comes up. So, in the case when you have a symmetric loss function, what happens? Well, if the loss function is symmetric, then this and this, they're equal, okay? So if they're equal, then when you're looking at this comparison, you can ignore them both. You just cross them both out, and you haven't changed the result of the comparison. So when you have a symmetric loss function, you can write the Bayes decision rule in an even simpler form. All it does is compare two posterior probabilities and say which one's bigger. I'm going to pick the one that's bigger. So again, there's a principle here that you want to memorize. When L is symmetric, you should pick the class with the biggest posterior probability. All right, so I know there's a lot going on in this lecture, but you see those two sentences that are highlighted in blue? If you only take two things out of this lecture, please try to memorize those two statements in bold blue. Those are the most important part of this lecture for sure. All right, so I said pick the class with the biggest posterior probability. That is a great rule of thumb to memorize, but I did condition it. It only works when L is symmetric. When L is not symmetric, then you have to include the loss functions after all. So then you can think of it as being weighted posterior probabilities. I'm taking the posterior probabilities, I'm weighting them with the loss functions and then comparing them. So that's a little bit harder to remember, but if you can remember this, then it's easier to then remember how to take the next step when you have an asymmetric loss. And just to complete this thought, in our cancer example, we can actually plug in the numbers in the table and figure out what the risk actually is. So for the purpose of this calculation, I'm going to use not the middle expression, but the bottom expression. So look at this expression here. We're going to plug in the numbers and use that to actually figure out what the risk is here. So in my cancer example, again, I'm sorry, I've got things out of order here. Let me... First, I have to say what the optimal decision rule is for the cancer example. So in the cancer example, the Bayes optimal decision rule is we're going to predict cancer if the number of calories is less than 1,600. Here, I'm going back to the symmetric loss, sorry. And the Bayes optimal decision rule is no cancer for x greater than 1,600. Now, you can also compute the risk for this optimal classifier. And that risk is called the Bayes risk. It is also sometimes called the optimal risk. And the Bayes risk is basically the risk of the Bayes classifier, or to put it another way, the risk of the best classifier you could possibly have. So in our cancer example, the Bayes risk is big R of little r star, which is, in this formula here now, plugging in this formula, I get this. So 0.249. And again, the Bayes risk is telling us that there is no decision rule that gives a lower risk than this. 0.249 is the lowest you can get for this data. So one thing that is interesting is that if we really know all of these probabilities, if we really know all the probabilities I've written down here, then we really can construct an ideal probabilistic classifier, the best one possible. The problem is that in real applications, we generally don't know these probabilities, at least not exactly. We try to estimate them. The best we can do is use statistical methods to try to estimate those probabilities. Now, when you are deriving the Bayes classifier, the Bayes decision rule, and then using it as a classifier, that is called risk minimization in both the statistical and the machine learning literature. And a lot of machine learning algorithms come down to risk minimization in some form, directly or indirectly. And so that's our basics of decision theory. Any more questions about that? Mm-hmm.
I wonder when we talk about the distribution of the random variables, do we mean do we mean it is only on the training set, or we consider the validation set and the training set?
When I talk about the distribution of the variables, am I talking about the training set or the test set or what? Well, unfortunately, all we really have access to is the training set. Therefore, we build a statistical model on the training set to try to estimate these probabilities, and that's all we can do.
So the R-star is optimum only for the training set, but may not.
Well, no. Let me be careful here. The R star here, that is the very definition of that, the very definition of risk, too, is assuming you know these statistical distributions exactly. So these are mathematical terms that give you a mathematical quantity that usually in the real world you do not have access to at all. And we have to face the fact that we want to estimate the risk, we want to estimate the Bayes optimal classifier, but we can't do it exactly. And so You should think of these terms, risk and Bayes optimal classifier, as being things that we aspire to but generally cannot achieve with real data. But you need to understand them because you need to understand what our aspiration is, even if we can't perfectly achieve it. So I do think that's a really important point. So let me just say one more time. Risk, with real-world data, you cannot determine the risk exactly, but we tend to believe that there is some pure ideal probability distribution that real-world events come from. And if we knew that distribution, we could risk. But we don't know it, so we can't. We want to approximate it. That's our whole goal this semester. All right, I want to come down to just a little bit of math review so that we can repeat what we just did with continuously distributed variables rather than discrete variables. I think that things like Bayes' theorem are easiest to think about when you think about discrete distributions first. Now we've gone through an example with this cancer example of a discrete distribution and doing risk minimization. Now it's time to get to continuous distributions, which are kind of the same ideas, only a little more complicated, because all of those summations become integrals. So now, instead of having a discrete probability distribution for x, we have a continuous probability distribution, which we assume can be specified as a probability density function, or a PDF for short. Something you've been hopefully thinking about a lot for the last 2 weeks, as you do homework too. A little bit of review about things you should already know about this. If you, hard to draw a straight line sometimes. Let's suppose that you have a variable x, and we have a PDF, f of x, that gives us a distribution over x. Maybe it looks something like this. Suppose that I choose a random variable from that distribution, and I want to know what is the probability that that random variable falls somewhere between x1 and x2. Well, the answer to that question is we want to look at the area under this portion of the curve. And that's our probability. So again, we have a random variable, capital X. We're asking what is the probability that it will fall somewhere between x1 and x2? Well, that's the integral from x1 to x2 of the PDF. That's what that shaded pink area represents, is that integral. And a reminder that the area under the entire curve is always 1. That's part of the definition of a PDF. You need to have the total probability of all events adds up to 1. So if you integrate from minus infinity to infinity, the whole PDF, you should get 1 always. Once we have a PDF, we can talk about things like the expected value of a function. Let's suppose I have a function g that I can apply to my random variable x. And I ask, what is the expected value of that over the whole distribution? Well, that is the integral from minus infinity to infinity of g of x, little x, times f of little x, integrated over all possible values of little x. And one extremely useful special case of that is, of course, the mean value of a random variable, which statisticians like to write mu, or expected value of x, is what you get when you do that integral where g of x is just x. And after learning mean, you learned about the variance, which statisticians like to write sigma squared is the expected value of how much we deviate from the mean squared. So random variable x minus mu, square it all, take the expected value of that. It's easy to prove that expected value of x squared and squared. All right, so given that, now let's come back to the cancer statistics. So let's suppose that x is now the number of calories that someone eats per day. And suppose now we can actually write a continuous distribution for that. And we discover that for people with cancer, here's the distribution of calories per day. And for people who don't have cancer, here's the distribution of calories per day. All right, let's just think about the 0-1 loss function for now. So we're not going to worry about false positives being better than false negatives. We just want a classifier that maximizes the probability of a correct prediction. So first of all, the wrong answer would be to look at where these two curves cross each other and say, oh, that's where I should put the decision boundary. And the reason, as before, is because we forgot to take into account the prior probabilities. So, suppose in our example, just to make it a little easier to graph, we're going to assume that now the proportion of people who have cancer is 1/3 rather than 1/10. And the proportion of people who don't have cancer is 2/3. And again, now we're using the 0-1 loss. So forget about asymmetric losses for a moment. So now what we're going to do is we're going to multiply by the prior probabilities. And of course, since there's twice as many people who don't have cancer, what that means is that this blue curve is going to come up to here. So the red curve is same curve as before, but now I've multiplied it by 1/3. The blue curve is the same curve as before, but now I've multiplied it by 2/3. All right, now, well, this is almost the posterior probability. To get the posterior probability exactly, I would need to divide both sides by px. But since that's the same number for both curves, I can ignore it. It's not going to change where the curves cross. So just this calculation suffices to decide where the decision boundary should be. And so in this example, the point where the two curves cross, that is the Bayes optimal decision boundary. And so what the Bayes classifier should do is, for everybody to the left of that decision boundary, you should classify them as probably having cancer. And for everyone to the right, you should classify them as probably not having cancer. So what the Bayes optimal classifier does is it just kind of looks at this chart. It looks up X on the chart, somewhere on that horizontal line, and then it picks the curve with the highest probability above that point. So pretty simple. Yeah?
Looking at the artifact in your drawing, but will there always only be one intersection? Because it looks like there might be another one.
Will there always be just one intersection? Generally, there could be more than one. Though when you have normally distributed data, things simplify a bit, and usually you don't have more than 2 intersection points, but you might have 2 points in your decision boundary. But in general, there could be any number. What's that?
What would you do in that case then? We just have like ranges of what you classify each thing as.
Yeah, then you're going to have multiple ranges of where you classify each thing as. Now, usually when we do this in practice, we're going to have not a one-dimensional feature space, but a multidimensional feature space. So that Bayes optimal decision boundary is going to be this complicated curve in high-dimensional space. It's not going to be just a finite number of points. But in the special case of only having one feature, then quite often the Bayes decision boundary is just one or a few points. Yeah? Well, we're just comparing these 2 posterior probabilities. Why is that the optimal decision boundary? Because it comes back to, back here, I worked out that this is how you can figure out the decision rule, and which comes from this expression for the risk. We're trying to minimize that expression for the risk, so that gives us this rule for deciding what the Bayes decision rule should be. So what I'm doing is, we're assuming right now that the loss function is symmetric, so I really just have to compare whether this posterior probability is greater than this one. And that is what this is doing here. This is comparing whether this posterior probability is greater than this one, modulo the fact that, remember I said that to have the true posterior probability you have to divide by px, but that's not going to change the comparison, so we don't actually have to waste time computing px in practice. Question? Blue shirt. Oh, I'm sorry. I did not mean to have 2 intersection points, so forget about that. But in general, you could have an arbitrarily large number of intersection points, and that's fine. That means that there are certain intervals where you pick cancer and certain intervals where you pick no cancer. Question? These are the PDFs, not the CDFs.
So why we not calculate the real possibilities for the variables, but we simply use the PDF instead?
I'm sorry, say that again?
Because I mean sometimes even their PDFs have the same value, but what we need is their possibilities, and we need to do the integrals for them, and for this part they may not be the same.
Well, we're not asking about people whose calorie intake is less than or equal to X. We're asking about people whose calorie intake is exactly X. So the CDF, the integral, doesn't play a role here. If that's not what you're talking about, maybe ask me after class. So I'm going to move on because I don't want to run out of time. We are going to now define risk the same way we defined it before, except, as I said, wherever I had a summation before, now we need an integral. Hopefully this looks kind of familiar from earlier in the lecture. But again, the summations are becoming integrals. And we can even write out the Bayes decision rule explicitly, albeit in a slightly confusing form, I guess. When we are computing the Bayes decision rule, the Bayes risk is going to be the area under the minimum of the two functions above. So what do I mean by that? Well, when you have a point in, well, if someone gives you a test point in this region here, we're going to classify that as cancer. And if we're wrong, the penalty we pay is essentially the integral underneath the blue curve, because that's the probability that we're wrong integrated over all of the different people who we might be tested on. On the other hand, if you go to the right side of that decision boundary, well, now we're classifying all those people as having no cancer. But again, the probability that we'll be wrong about that is specified by this red curve here. So the area under the minimum of the blue curve and the red curve, that is what we're looking at now. That's the Bayes risk. And so, again, assuming that our loss function is sane, meaning that correct predictions are not punished, then the Bayes risk is going to be the integral. Well, we're going to integrate over all points x in the two PDFs. And for every single one of those infinite number of points, we're going to choose the y, either equal to 1 or equal to -1, that minimizes this expression. So that's going to be the Bayes risk for the continuous problem. Notice I've put the loss function back in. When I was doing these graphical examples here, I was using a 0-1 loss, just to keep it simple. If you want to use an asymmetric loss, then you're going to be scaling the two curves, the red curve and the blue curve. Again, you're going to be scaling them to also incorporate the loss function. But then you'll do the comparison in the same way. It's just that your curves will be rescaled. Now, a very nice special case, which again is the most common case, is that we're using the 0-1 loss. And if we are using the 0-1 loss, then the risk has a particularly nice interpretation, which is it's the probability that our decision rule is wrong on any randomly chosen test point from our distribution. Which makes sense because the risk is the expected loss. The expected loss, if the loss is just 1 when you're wrong and 0 when you're right, the expected loss is the probability of being wrong. And also, assuming we're using the 0-1 loss, the Bayes optimal decision boundary so the posterior probability, you can think of that as being our decision function. And 0.5 is the ISO value we're going to use in that to find the decision boundary. So let me give you an example of what that might look like with a two-dimensional feature space. All right, so what we have on the left is, again, there's 2 dimensions of our feature space. And then the third direction, what this shows us is actually the class conditional distributions. So the probability of a specific x given the class y, where we could say that the red, for instance, is y equal 1. The blue is y equal minus 1. So in this particular example, what we've done is both classes have Gaussian distributions. But the Gaussian distribution for people with cancer is different than the Gaussian distribution for people with no cancer. And so, if I want to classify a person who I don't know, someone who you give me their 2 features, let's suppose that you give me a point right here. What I do is I look up and I say, which is higher at this point, the blue function or the red function? Well, at that point, the blue function is above the red function, so no cancer. And you can actually see the decision boundary is where the blue curve and the red curve meet. So this example shows that, in higher dimensional feature spaces, the decision boundary, of course, is not just a point or a few points, but infinitely many points. On the right-hand side, I have plotted exactly the same 2 functions. There's this, it's now a contour plot instead of a 3D plot. And so you can see the isocontours of the no cancer function here. You can see the isocontours of the cancer distribution here. And again, you can see the decision boundary here is this white line. And so that's what's implicitly computed by the technique, the algorithm that we will learn on Wednesday, which is called LDA. So don't worry yet about how we get these curves. You'll learn that on Wednesday. But before we go, I want to make sort of a final declaration. Taking a step back and taking a meta look at what we've learned so far, we can get out of this 3 different ways to build classifiers. And the first way is what are called generative models. And an example of a generative model we will learn on Wednesday. It's called linear discriminant analysis. The way that generative models work is a sequence of steps. First of all, we're going to assume that the sample points, say people who have cancer, all come from some probability distribution. And the sample points, people who don't have cancer, come from a different probability distribution. We are going to take the data, and from that, we're going to guess the form of the distributions. So what LDA does is it just guesses that they're normal distributions. Once we've established that, we want to figure out the parameters of that distribution. And we do that separately for each different class. So pick one class, like people who have cancer. Take the data you have representing the people with cancer and fit distribution parameters to that class. That gives us what are called the class conditional distributions of the form, PDFs of the form fx given that y is in class C. Then for each class C, you also need to estimate the prior probability. Once you have those 2 things, you can use Bayes' theorem to get the posterior probability. And lastly, I'll assume that we're doing 0-1 loss. You pick the class C that maximizes the posterior probability, the probability of being in class C for test point X. Now, that is equivalent to maximizing the class conditional distribution value times the prior probability. So that's the most complicated of these 3 types of models, in a sense. There's another approach to this, which is called discriminative models. And an example of that we'll see in about 2 weeks is called logistic regression. Logistic regression is a little bit like LDA, except it says, let's skip all those early steps and just model the posterior probability directly. So we're going to try to estimate the posterior probability without estimating the class conditional probabilities or the prior probabilities. Kind of do an end run around the hard parts. And the third model we could do is just a blunt tool for finding a good decision boundary that does not actually give you probabilities at all. And that's a description of support vector machines. So there you just model the decision rule R of X directly, and you don't even try to estimate a posterior probability.